Okay, hello everyone, welcome back. So, last time we were talking about empirical formulas. So, when you have information about the relative mass of carbon and hydrogen, you can figure out the the empirical, or what we call molecular formula. So, this ratio we just determined, 1 carbon to 4 hydrogens, is for that's for the empirical formula. So that's how we figure out the empirical formula. So now if we had the molar mass, we can use this information. If we had the molar mass of the actual compound, we can use that along with this empirical formula to determine the molecular formula, the actual formula for the compound of what we're interested in. But this time, this is just the empirical formula. And sometimes the empirical formula and molecular formula are the same, but we can't know that unless we know the molar mass of the compound. So, if we think about the chemical formulas, a lot of compounds can have the same empirical formula as another compound. For example, if we had a molecule like C2H8, which is ethane, so ethane. This is propane. And this is butane. You see here, they can be reduced to a simpler fraction, or let's say simpler notation here. C2H8 can boil down to CH4, C3H12, CH4, and C4H16CH4, and they all have a common denominator of 2, 3, 4, respectively. Okay? So that's empirical formula. Okay, let's try another example. Vitamin C, found in citrus fruits, can be obtained from dietary supplements. So if you don't want to eat the whole fruit, or like eat a bunch of fruits every day without the sugar, you take vitamin C tablets. So let's calculate the empirical formula for vitamin C, which is 40.9% carbon, 54.5% oxygen, and 4.58% hydrogen by mass. So the second part of this question is use the fact that the molar mass of vitamin C is 176 grams per mole to determine the molecular formula for vitamin C. Again, this should be say formula, not formulas, for vitamin C. And for this example, let's say we have a 50-gram sample of vitamin C available. So let's break this information down. So let's convert each element to grams. So we have 50 grams. So let's try like 3 sig figs. 50 grams of vitamin C. So we have a 50-gram sample. And in that sample we have 40.9% is carbon. So to represent as a percent, we need to determine, so out of 50%, so if it's by 50, and usually, 40.9% is out of 100, we need to divide the value by 2 to give us an equivalent fraction here. So 40.9 divided by 2 is 20.45. So if we do 20.45 divided by 50, we will get 40.9. We will get 40.9 grams again. Well, actually, it doesn't matter actually, because they will cancel out anyway. But it might be best to just use a 100-gram sample. But just for simplicity's sake, you won't always have a 100-gram sample. So it's best to just take this and do and use this as a different example. Okay. So let's do, so 50-gram sample, right? So So we actually had to divide this by 2 since we since our sample size is now 50. Another thing you can do, maybe let's do it a little differently. So sorry about that. So to figure out how much grams out of 50 is 40.9%, what we can do is convert 40.9 to a decimal. So I just divided my percent by 100. So we're going to times 50 gram sample. And that will give us our fraction here. That will give us the amount of mass, not a fraction, but the amount of mass that is carbon. So we get 20.45. Carbon. And then we do the same thing for oxygen. So we're going to multiply this by 50.0 grams. So we get oxygen 54.5% equals 0.445. Okay. 545, I mean. So we get 27.25. And then lastly, we have 4.58% for hydrogen by mass. So this is 0.0458 times 50 grams. And we get 2.29 grams. Okay, so now we have the grams of hydrogen, oxygen, and carbon. That's good. So now we need to convert to moles. All right, so let's start with carbon, 20.45 grams. Carbon times 1 mole, 12.01 grams carbon. Okay. So let's first do our carbon example. And we get 1.70275. So let's just keep a few extra digits here. But we're probably going to use, if we know for a fact percentages, we're probably going to use 3 sig figs. Okay. Now for oxygen, 1 mole of oxygen is equal to 16 grams of oxygen. So we get 27.25 divided by 16. We get 1.7. 1.703 125. Sorry, not grams, moles. Let me put my units here. And lastly, we have, sorry, I need to write a little bit smaller or give myself some more room here. 2.29 grams of hydrogen times 1 mole hydrogen is equal to 1.01 grams of hydrogen here. And then we get roughly, maybe a little bit less than 2.29. 2.29 divided by 1.01. So yeah, 2.26. 26733 mole of hydrogen. Okay, So I didn't give myself enough room here, but we're going to find the simplest whole ratio by dividing by the smallest number of moles. So let's just write our elements here: carbon, oxygen, hydrogen. So carbon, we have 1.70275. So that's the smallest number, so we're going to divide itself by that number. So our ratio for carbon is 1. Our ratio for oxygen is very close to the ratio for carbon. So we're going to, the number is probably going to be close to 1. So we're just going to say that's 1 as well. Okay, because it's very close there. It's going to be very close to 1. And if we do the actual numbers, the math here, 1.703125 divided by 1.70275, we see that it's essentially 1. Then hydrogen, we divided by 2.26733 divided by 1.70275. And let's see what we get there. 2.26733. And we get roughly 1.33. Okay, so our ratio is so now let's find our ratio here. So the empirical formula. So I should have gave myself some more space, but let's just write the empirical formula first. So right now our empirical formula should be C1H1.33 and then oxygen 1. So now this fraction here, or this formula is not very helpful because we have a fraction, we have a decimal point there. So we want to actually find a way to get rid of that 1.33. So if we did 1.33 times 3, sorry, not times 6, times 3, it gives us about a ratio of 4 to cancel out the 1.33. Yeah. So what we want to do is calculate this and multiply everything by 3. So we get C3H4O3. Okay? So we're multiplying by 3 to get rid of the mixed number there. So this mixed number is 4/3. So this is equal to 4/3. So we multiply by 3 to get rid of that denominator of 3 there. So we get C3H4O3. Okay. So now we need to determine, so we determined the empirical formula. So this is our first part of our answer. So you would highlight this, say this is my empirical formula. Empirical formula. And then we need to find the molecular formula. So we're going to first calculate the molar mass of my empirical formula and then divide it. Then divide the molar mass by this value. So let's calculate this molar mass. So C here has 3 times 12.01. Hydrogen is 4 times 1.01. And oxygen is 3 times 16. So for molar mass, we simply add up all the atoms and multiply each atom by their molar mass, find the sum of all the carbon atoms, sum of all the hydrogen atoms, and then find the sum of the oxygen atoms. And then we just take the absolute sum of all of them, and we will get a value of, okay, so let's do this, 12.01 times 3 plus 4 times 1.01 plus 48 for 16 times 3, and we get 88 0.07 grams per mole. Okay, so now we have this value. And we know the molar mass. So we know the molar mass here is, so the molar mass is 176 grams per mole. So when I do grams per inverse mole, that means grams per mole. So you can write it on the same line and you're not having too many fractions to deal with. So we go up here, it says 176 grams per mole. So we're going to use that value. Take that value divided by the value you just calculated in the previous step, 88.07 grams per mole. Okay, and then this is going to give us a whole number. So if we do that, 176 divided by 88.07, that gives us 1.998, or essentially 2. And we're going to now use this factor here and multiply our empirical formula, C3H4O3. So we're going to now multiply this value by 2. Maybe I should put this on a separate line so it's not confusing. So we're going to multiply this fraction by 2 here, and we get C6H8O6. And if we looked up vitamin C, here, we'll see its empirical, or sorry, not empirical, its molecular formula is C6H8O6. So we are correct. So that's how you figure out empirical formula and molecular formula. Okay, are there, I was about to ask, are there any questions? But this is a recording. But in class, I would ask, are there any questions? And we could go over some of it if students wanted to. Okay, so go through those examples. You should be printing out, or taking this blank outline and filling out the outline as we go through the lecture. I think that's really helpful for problem solving. Not just absorbing information. Many students have different ways of learning, so I try to make lectures that kind of incorporates all the 3 different learning styles, or all the different learning styles. Visual learner, auditory learner, or maybe by like writing things down. Like you need to write things down to internalize or kind of mentally absorb the information. That's why I primarily don't do PowerPoint, just because the information tends to go through one ear and out the other, and there's really no learning going on. All right, so let's move on here. Now we're going to start balancing chemical equations. So we've learned about the mole, the grams, how to calculate formulas and figure out percent composition based on combustion analysis. So now let's talk about balancing chemical reactions. Okay. So glucose, also known as blood sugar, is our primary source of energy. The bloodstream delivers both glucose and oxygen to tissues and other functions of the body that requires energy to function. So the reaction is they react. So they deliver this oxygen and glucose, where they react to give a mixture of carbon dioxide and water. So that's the energy transformation process. So once this blood glucose travels through the bloodstream, and oxygen is always in the bloodstream because of hemoglobin, and that's what helps the tissues absorb energy, is chemical transformation. So biology always is a kind of cool symbiotic relationship with chemistry. Just like how chemistry is in a pretty good, if we don't understand the physics of chemistry, we wouldn't understand, chemistry itself, and then in turn the application of chemistry, biology. All right. So balancing chemical reactions can be difficult. However, when you're used to balancing chemical reactions, it becomes easier, kind of second nature, but there are some tricky ones. Okay, so the first tip I tell my students is we should try and balance elements that may appear in one or two places in the chemical reaction. In this case, let's balance carbon. And we'll balance carbon. So the way we do that first is we notice that there is 6 carbon atoms on the left. So we should put 6 carbon atoms on the right in front of CO2. Okay, so now the carbons are balanced. Okay, so we'll continue the rest of this in the next video. So I'll see you then.